Today we'll be discussing graphic equalizers, which are multiple bandpass filter banks. Before we do, let's analyze what a signal looks like in the time domain versus in the frequency domain. So if we have a sinusoidal signal given by some voltage with respect to time, it looks something along these lines. It has an amplitude of A and a period of T, where T is the difference between any 2 points that are identical on this signal. So this might look like A times sine of 2 pi times F times T, where the period of the signal is the period of this repetition. So let's say that T was equal to 1 second. That would correspond to F equal to 1 over T of 1 hertz. T was equal to 1 millisecond, 1,000th of a second, then F would correspond to 1 kilohertz. Examining this in the frequency domain, we would see that VO of F plotted versus frequency, we would have a single tone at whatever our frequency was, and whatever the negative of our frequency was, that had an amplitude of A over 2. Now so far we've been looking at filters that can only select either a low pass or a high pass version of the signal. In other words, we can have a frequency response that starts off attenuating the signal and then passing the signal, or we can have a frequency response that starts off passing the signal and then attenuating the signal at higher frequencies. Today we're going to examine bandpass filters. I'll abbreviate this BPF. A bandpass filter is a combination of a high pass and a low pass filter. So imagine that we have a filter that has a frequency response H1 of F, so it has some frequency, some function of F that looks like this. It has a peak value of 1, and it goes down to a minimum value of 0. So at low frequencies, signals pass through this filter quite well, and at high frequencies, signals get attenuated by the filter. In other words, over here, signals pass through the filter with little change, and over here, signals pass through the signal with significant change, or diminution of their amplitudes. Now we also looked, so this is H1F is a low pass filter, LPF. We also looked at filters that had functions like H2 of F, where they start off being attenuated at low frequency, and at high frequency there's very little attenuation. These filters are called high pass filters because they allow high frequency signals to pass through them. Now a bandpass filter is kind of like the product of these two filters. So if we were to plot a function H3 of F that was the product of these two filters, we would get a response that looks something like this. The center of that filter would be called the center of the bandpass filter, the center frequency of the bandpass filter. And we see that at low frequencies, there's a lot of attenuation. In the center of the band, there's very little attenuation. And then again, at high frequencies, there's a lot of attenuation. For an audio system, we'd like to take multiple of these filters so that we can highlight different parts of the audio spectrum. So if you recall, the audio spectrum ranges from around 50 hertz up to around 20 kilohertz, or 20,000 hertz. And this is just based on what human beings can typically hear. Some people hear a little bit lower frequencies and some people hear a little bit higher frequencies, but average range is somewhere in that ballpark. Now we can also think that this might be segmented into different instruments. For instance, we might hear drums banging that have frequencies that are closer to 50 hertz. We might hear piccolos that have frequencies that are closer to 20,000 hertz. And what we'd like to do for recording, or if we're listening to music to hear a certain quality, is to highlight the sounds that we'd like to hear and to attenuate the sounds that we wouldn't like to hear. And to do this, we use what's called a graphic equalizer. So you can imagine that instead of having one filter, I have N filters that are centered at different frequencies. For instance, 100 hertz, 200 hertz, 400 hertz, 800 hertz, and so on. Every time that we increase a frequency by a factor of 2, that's called an octave. And for those of you that are familiar with musical instruments, you know that every 8 piano keys, the frequency doubles, so you have 1 octave of frequency increase for every 8 keys of a piano. Now we might like to make filters that center around each of these frequency bands. And we'd like to be able to adjust their amplitudes up and down so that we can highlight different frequencies. For instance, we might have a musical instrument or a type of music that's playing that we want to highlight. If we're listening to classical music, we probably want the whole range to be fairly flat because we're listening to different instruments at different frequencies. But if we're listening to something along the lines of hip-hop, we might like to highlight the lower frequency range because those are the sounds that are typically highlighted in hip-hop music. Now the way that we make this filter is we have an audio signal and we split it up into N different paths depending upon how many filter banks we'd like to have. So we're going to go from a filter that has a frequency response Hn of f and one that has a frequency response of H1 of f. You can imagine that perhaps this filter had a center frequency of 100 hertz and the Hn of f filter has a center frequency of 20,000 hertz. So we're going to cover the entire audio spectrum. Now we'd like to be able to program the gain of each of these, so we use a programmable gain block that has a programmable gain of G1 and a programmable gain block that has a programmable gain of Gn. And at the output of all these programmable gain blocks, we'd like to send all the signals and recombine them with the summation block and send the signal to a speaker or other audio load. Now we'd like to be able to individually program G1 between 0 and 1 and program Gn between 0 and 1. And you can imagine that when G1 or Gn is equal to 0, so if any of the G sub n's is equal to 0, we get minimum signal out for that frequency. And if we set any of the Gn's equal to 1, we get maximum signal out. And anywhere in between, we get something in between. Now, we can do this with analog circuits, but we can also do this using signal processing techniques using the LabVIEW tools. Shown here is a LabVIEW program that consists of that is a graphic equalizer. We use a DAC assistant to take a signal coming that's input to the MyDAC, and we split that signal into multiple filter banks representing different frequency bands. We can program the gains of these filters using a front panel that has sliders that we can change dynamically. And in doing so, we can change the frequency response of any music that we're listening to. Following this, we sum everything together and send it back to the output, and also send it to a spectrum measurement tool. Now, we can listen to a sample of how this instrument works. Right now, we're not letting very many different frequencies pass, but we can selectively increase. And you see, as we change different frequency sliders, the frequency response changes. And also the sound quality that we can listen to changes. In the lab, you'll be building this graphic equalizer and front panel. And playing around with the sound yourself to see how a recording engineer might control sound.